Okay, so my name is Inbar, and I work at Taboola. And about, about 3 or 4 years ago, I was working on a project with a goal to help doctors to make better predictions about which medications we should give to patients with epilepsy. So the idea was to be able to say when a medication stopped working, why it's not working anymore, and whether we need to increase the dose of the drug or we need to change the medication, and maybe even be able to predict which medication would be the best fit for the specific patient. So we got some pretty decent results for the first phase of the project. And about this point, one of my advisors, which was a doctor, told me, you know, this is all really nice, but I know doctor. You can't just give them black boxes and tell them, just trust me. It just won't work. So we need to be able to understand why the model says this and that, or at least be able to understand if it's unconfident of its prediction. So deep learning was already a big hype back then, and it got some really good results for computer vision applications and for speech recognition. And people started applying it to other domains as well. And since a lot of my time on this project was dealt with engineering features based on EEG, I started wondering whether, given enough data, we could be able to use deep learning for this project as well, but without making the black box problem that we had even bigger. So I started digging into uncertainty in deep learning, and I stumbled across a lot of papers from the 90s, but I didn't find much going on back then. And this was the situation up until about 2 years ago, and this is what I'm going to talk about in this talk. So first of all, I want to talk about why we should even care about uncertainty. So one example is at high-risk applications, like I just described. So for applications in medicine, and sometimes even in finance, we really want the model to be able to say, you know, I'm not confident about this. I'm not sure. Maybe it's better to give some human expert to take a second look at this. Another example is out of data samples. So if we took a network and we taught it to distinguish between pictures of a cat and pictures of a dog, and then we said, here's a picture of a monkey. What do you think? Now, since the network only knows dogs and cats, for sure it's going to say one of the two. It's going to say it's either a cat or a dog, because that's the only thing that it knows to do. But what we would really want the network to do is say something like, you know, I have no idea. I've never seen anything like that. Another situation where it could be useful is for time series prediction. So for instance, we could teach a network or any model to work on time series, but we want it to be able to say, this point is just too far from what I've seen, so I'm not confident about it at all. Lastly, it could be very useful for us as practitioners because it gives us a lot of new possibilities to debug the network. We could, for instance, use uncertainty for error analysis. We could take a look at the samples that the model got wrong, but with very high confidence. And these are examples that we really want to try to figure out what went wrong over there. But we could also be interested in examples that were OK, but with very low confidence, and see if we can boost the confidence of the models for these examples. OK. So I'm going to talk about uncertainty types, which types of uncertainty exist. And then I'm going to give a really brief introduction to Bayesian learning, and I'm going to talk about neural networks from a probabilistic point of view. And then I'm going to talk about model uncertainty and data uncertainty. So this is a bit of a spoiler for the first bullet. But I'm going to talk about those two types of uncertainties and what can we do to model those two types of uncertainties and to incorporate it into the model. OK. So some of you at the moment might be wondering, OK, what about softmax? OK, no. First, let's talk about which type of uncertainties. So it's common to talk about two types of uncertainties. The first type is aleatoric uncertainty, which captures the noise that is inherent in the data. And this is further divided into homoscedastic uncertainty, which is constant for all the data, and for heteroscedastic uncertainty, which says that some inputs might have noisier outputs than other inputs. And the second type of uncertainty is epistemic uncertainty, which is uncertainty about the model itself. And this uncertainty can be explained away given enough data. So it means that if we see enough data, we could be more confident about the model that we have in hand. And this is not really surprising. But this is opposed to this type of uncertainty that lies within the data collection process itself. So it doesn't matter how much data we're going to collect, we won't be able to reduce the this is the first type of uncertainty. So epistemic uncertainty is usually we're going to talk about uncertainty in model parameters, but we can also talk about uncertainty in the model itself or the model structure. And I'm going to just refer to it as data uncertainty and model uncertainty. OK, so now some of you might be wondering, what about softmax? Because softmax is a function that we give it a vector of scalars, and then it gives us a vector of probability. So we could think that if we're going to look at the probability that the network gave for a specific output, for a specific label, and we see that this label got a very high probability, then it means that the network is very confident that this is indeed the true label of the sample. OK? But this is, in fact, not true. And the reason that it's not true is because what happens when we give the network the order to work with the softmax? We actually say, you have a certain amount of confidence, and you have to divide this confidence between the different labels. So it's kind of pushing the networks to say something. And then it might say something like, well, if I really have to, then I'm going to bet on this guy and maybe a little bit of this guy and this guy. But maybe it's not confident of anything at all. Maybe if we could just let it tell us whatever it thinks, it would say, you know, I really have no idea. So we could get a vector with very high probability for a specific label, but the confidence of the network in this entire vector probability would be low. OK, so we can't really trust on softmax to give us the uncertainty that we want. Luckily, we have Bayesian learning, and people have been using Bayesian learning to get uncertainty for a very long time now. So I'm going to give a really, really brief introduction, just because if somebody is not familiar with it, it's going to be very hard to follow the rest of the lecture. So Bayesian learning, think of probability as a measure of belief. This means that we have some belief about the world. It could be belief about which model generated the data, or what are the parameters of the model that generated the data. And this belief is represented using a prior distribution over, for instance, the weight. And learning in Bayesian way just means that we update the belief. We update the prior distribution as more data comes. So when we see more data, the prior distribution becomes the posterior distribution. And we do this update using Bayes' law, which is why it's called Bayesian learning. So as we see more data, we can calculate the posterior, and then it's going to be the likelihood of the data given the weight times the prior over the weights, and this is all divided by the distribution over the data. OK? So this is Bayesian learning in a nutshell. Now let's think about neural networks from a probabilistic point of view, because usually when we talk about neural networks, we think of them as something that want to minimize some sort of loss function. But we could also think of a neural network from a probabilistic point of view. We could think of a neural network as a probabilistic model that just tries to find the distribution of y given the data and given the weights. And this way, if we want to learn the correct weights, what we're going to do is try to calculate the maximum likelihood estimation. So it means that we're just going to find the weights that maximize the log likelihood, that maximizes the probability of the data given the weight. And since we assume that all the samples are ideal, we could just break this and take the sum out, and then this is what we're going to work with. Okay? And alternatively, we could add regularization, and then instead of learning MLE, we're going to learn maximum a posteriori. We're going to learn map estimate. So this way, we're going to find W that maximizes the log of the posterior distribution. Okay? So you can think about it as sort of regularization to do the same thing, but with adding regularization, if you look at these two examples. OK. This is all the introduction that we need. Now let's talk about model uncertainty, which is, most of the talk is going to be about this uncertainty. So when we talked about neural networks from a probabilistic point of view, we still didn't say anything about uncertainty, because we output the best weights. We wanted to look for the weights that are best for our minimization problem. But alternatively, we could say we are not confident of the weight. So instead of just outputting one set of weights, let's output an entire probability over the weight. And then we're going to start with some prior over the weights. And at learning time, we're going to update this prior, just like we did in Bayesian learning. We're going to update it to the posterior distribution, again, over the weights. So we're just going to calculate the likelihood times the prior over the weights, and this is divided by the data. And at prediction time, what we want to do is, instead of taking the one set of weights that we have and calculate the prediction, we're going to integrate over the entire set of possible weights. And for each weight, we're going to calculate the likelihood times the posterior distribution of this weight being true, given the data that we've seen. OK? Was that clear? Cool. The only problem is that the posterior is intractable for pretty much any problem or any interesting problem that you're going to work with. So it means that we can't really compute this integral. So I just said something, but we can't work with it. Luckily, this is not something that's unique for neural networks. This is something that you're going to stumble across pretty much in any application that you want to try to work with Bayesian learning. The intractability of the posterior is just something that comes back and back to us. And this means that there are also ways to solve it that are not related to neural networks. And we can use them for our problem. So we can divide the solutions to two families. One family is sampling method, and the other one is variational inference. So just to iterate, because it's really important that it's going to be clear, we have a problem that we have a posterior that is intractable, and we want to be able to use this posterior somehow. OK, so one way would be, OK, we can't really calculate the posterior itself, but instead of calculating the posterior, let's sample from it, because some distribution we could sample from, even though we can't really calculate them as is. So let's sample some examples from the posterior distribution. And then whatever it is that we're interested about, whatever it is that we want the posterior to do, we would just calculate this using the samples that we draw. The second option to use would be variational inference. And then this is just saying, well, we have one distribution that is interesting, but we can't really calculate it. And we have a different, so let's instead find a different distribution that we could use, we can do calculations on, and is as similar as possible to the first distribution that we're interested in. I'm going to talk about it later, but I just want to emphasize, in terms of bias and variance, which is very common to talk about in machine learning in general, this method has a very high bias because we choose the variational family. So we already introduce a lot of bias into the method. But it has a low variance, but this method, it doesn't rely on any assumptions that we make. So it doesn't have bias, but it has very high variance. And if we're going to repeat it several times, we're going to get different results. So most of the methods I'm going to talk about are going to be from this family. And then I'm going to briefly mention something from here. So just to dive a bit deeper into variational inference. In variational inference, we have a target distribution. In our case, it's the posterior distribution. And we want to use it, but it's intractable. It means we can't really calculate the integral over this distribution. And what we're going to do is we're going to approximate it with a different distribution. Let's call it Q, which is from a tractable family. And we want to find Q that is as similar as possible to the posterior distribution. And when we talk about similarity in distribution, we usually talk about KL divergence. So KL divergence, you can think about it just as a measure of how similar one distribution is to another. And this is just the definition of it. OK? Now let's see what we can do with it. Let's assume that Q, the probability the variation probability that we want to use, is parameterized by theta. So we want to find theta that minimizes the KL divergence between Q theta of W and the posterior distribution. So this is just opening the definition, using the definition of KL divergence, and just opening the posterior distribution using Bayes' law. And you can see that this part over here is not dependent not on theta and not on W. So it's a constant in our minimization problem, so we don't really care about it. So we can remove this, and we can break this entire thing using log laws, and then we can break the integral into two parts. Now, if you didn't really follow, it doesn't matter, because here comes the interesting part. This is what's important. Let's see what we got. The first part here is just the KL divergence between Q theta and W, but with the prior instead of the posterior. So now we're interested in the KL divergence between Q, our variational probability, and the prior. And this over here is just the expectation of the log likelihood with respect to the variational distribution. OK, so it's just the KL divergence between Q and the prior, and the expectation of log likelihood with regard to Q. So it means that our minimization problems just becomes some trade-off between trying to find Q that fits the data as good as possible, finding Q that gives very high likelihood to the data that we see. But on the other end, we want Q to be as simple as possible. And now we say that simple as possible means that we want it to be as close as possible to the prior distribution. OK, so this is just another way of doing regularization in neural networks. This term tries to fit the data. And this term is responsible for the regularization. OK?
When you say that we're trying to minimize the field divergence between Q theta and the prior distribution,
yeah.
Is the prior distribution something we set ourselves?
Yeah. Okay. And usually we keep Q something very simple. It could be some, yeah, some Gaussian, for instance. OK. So now that we have Q, we could just take it and put it in the integral that we had earlier that we couldn't compute. And now we can compute it because we found Q that is tractable. OK? So this is how we make predictions. That's it. And this is work that's been done by Google DeepMind in 2015. But the same ideas were also presented by Graves in 2011. And it even goes back to 1993 with Hinton and Van Kamp. And last year at NIPS, there was a workshop about Bayesian deep learning. And the opening talk in this workshop was a very nice talk about the history of Bayesian neural networks. And it just goes over the same ideas that goes back to the 70s. So it's really nice to see how those ideas kind of evolved to what we see today. And it's like 40 minutes talk, and it's really simple to follow, and I think it's really recommended if you're interested in these kind of things. I'm going to just skip this part. OK. So now you can say, OK, but I don't want to train the model from scratch. I don't want to make, I have my neural network. I'm comfortable with it. I know what good loss function works for me, because I've tested a lot of loss functions, and I've tested a lot, all sort of things. And I don't want to change my loss function. Is there a way I could take the network that I already have and get uncertainty estimations from it? Can I even do that? So can I do that? Well, it turns out that if you use dropout during training, which a lot of applications do, then you actually can. And this is a really nice work that's been done by Yarin Gal from Cambridge University. And I'm not going to go into the mathematics here. But he says that if you're going to choose Q to factorize over different matrices Wi, where you can think of each matrix to be to correspond to some layer in the network, and each Wi is calculated as a multiplication between mi and a diagonal over variable zij, where each zij is in turn this sample from Bernoulli distribution with pi, then we get exactly dropout. And why is that true? Because you can think about zij as something that just chooses if the j unit in the ith layer in the network is going to be dropped. And that's exactly what we do in dropout. So using this way of interpretation of dropout, we can get a new way to think of why dropout works. Because usually when we talk about dropout, we say that it works because it adds noise to the trading procedure, and then we can avoid overfitting. But this suggests that dropout works because it approximately integrates over all model parameters instead of just taking one set of weights. Now, let's say that you have a network with dropout. What can you do to get uncertainty estimation? At test time, instead of just scaling the parameters like you usually do with the dropout, you're going to do exactly what you do at training time. You're going to do dropout. You're going to take random units, choose units at random, and remove them from the network. And then you're going to get a prediction. And you're going to repeat this procedure t times, and you're going to get a sample of t predictions. You can calculate the mean of this sample, and this is going to be the prediction. And the variance of the sample is going to be the uncertainty estimation.
So does this grade the performance of the network?
Yeah, so a lot of the criticism about all of the things I'm going to talk about is that it's really, really high. It's really hard to do it when you have application that needs to be very online, that need to work very fast. And that's true. And that's a lot of the problems with those things. But still, I think at least for practitioners, when you try to debug your model, you could use it, even if you can't really use it at test time. And some applications don't need to work that fast, and you can say, OK, I'm OK with being a bit slower, but being more reliable.
But I didn't mean like at speed. I meant at performance.
So not necessarily, because nobody guarantees you that the last weight is the best. Okay, you can think about it as when you do optimization, then you start to work your way through the loss and until you get to a specific area. And this is an area that is good for you. But it's not necessarily, it's not guaranteed that the last point that you're going to get in this area is the best. Maybe you want to get, but even not in terms of global versus local minimum, some people says that maybe you want to get some estimation of the entire area that is good for you and not just one point from it. And
what's the relationship between the dropout probability and the actual root mean square of the error that you're looking for in the output.
What do you mean?
You're looking for the uncertainty of the output of the model. But
Yeah.
the more you reduce you increase the probability of dropout.
Yeah.
The error
Then it's going to be more.
is going to grow.
Yeah. So the more you take more units at dropout, then you're gonna get the variance is gonna get bigger. But this is something that's true for dropout in general. So
yes, but how do you know how this relates to the actual uncertainty of the result?
I still don't understand the
You
question.
have a scaling here. If you drop out more, you get more uncertainty.
Yeah. So he said, well, you said, let's take dropout and use this thing to calculate uncertainty. But if you take dropout with higher, rate, then you're going to get more variance, and then you're probably going to get a less certain model. Did I understand you correctly?
Yeah, uncertainty.
Okay, so I'm going to think about it, and we'll come back to it later.
Some kind of a ratio between the dropout you give and the resulting uncertainty.
I think what he means by that is that you want to take the model that you have, which you chose the dropout not as a way to measure uncertainty, but as a way to optimize your model. And then it's usually like 1.5, which is what usually people talk. And then you get this network, and you want to try to assess the confidence of this model. You don't want to choose the dropout for this. Okay, so given that you already have a network that was trained on dropout, you could use it. This is a nice example that he has. You can see it on his blog, where he trained a very small network to do dropout with dropout, and it's supposed to fit the regression problem. And in the blue, you could see the mean of the sample, and this is one sample. And the shaded area is the confidence. So you can see that when we have more data points, our confidence is better, okay? Because this is the standard deviation, so the standard deviation is smaller, which means that our confidence is larger. And he has some really nice demonstration in the side where you can add more points, and you see how this affects the uncertainty. So it's really nice to play with it if you want. Okay, this was about variational inference method. And now I want to talk briefly about Markov chain, about sampling methods. And one of the most successful or most famous sampling methods is Markov chain Monte Carlo, where you would construct a Markov chain where the desired probability, the desired distribution that you have in mind, the distribution that you try to sample from, is the equilibrium distribution of this Markov chain. So it means that we have some random process that you get samples from, and as we draw more samples and as we update the model, we get samples that are from the distribution that we wanted. So in this way, we mean that we're going to use MCMC to get samples from this posterior distribution, and then we're going to get those samples, and we're going to use them. So we have samples of weights, and we're going to use each weight to get prediction, and we're going to just average the predictions from the different samples at test time. And again, you might think, OK, so what this have to do with deep learning? It sounds really different than everything that we're doing in deep learning. But as it turns out, and this is a really cool paper, that if you just by adding noise to the parameter update, you get something that approximates MCMC algorithm. So let me just be clear. This is standard SGD for map estimate. So we take a standard SGD. We take the network that we have, and all we need to do is at the update step, we're going to add some noise. And by adding the noise, it's guaranteed that theta is going to converge to the posterior distribution. And that's really cool because it means that we can just sample from the final distribution that we have, or we could just take weights from the last phase of the training, and we could use them to make predictions and just do model averaging as we did before. OK, so this was about model uncertainty. That was the main part of the talk.
How do you know how much noise you should add?
So they said that you should scale the noise as you progress with the steps. So the larger the step, you need to make the noise a bit smaller. I just didn't want to get into it, but it's in the paper, so you could just read it. OK. So data uncertainty. Sometimes we don't want to just calculate the uncertainty in the model. We want to capture uncertainty that we have in the data. So sometimes, for example, our labels might be noisy. So this is a work by Alan Becker from Bar-Ilan University. And what they said is, let's assume the true label are passed through noise channel with unknown parameters. And all they did is add an extra noise layer to the network. So you take a regular network and you just add another layer which needs to capture the noise. And then let's look at the likelihood, what it becomes. So the probability of the scene label, the label that we see, to be j given x, w, and theta, which is the parameter of the noise, is going to be a sum of 1 over k, where k is the number of labels that we have, of the probability of the scene label to be j, given that the true label is y. So we have a true label, but we have some null, so maybe the label that we see in the data is going to be different. So the probability of the scene label to be j, given that the true label is y, and this is all multiplied by the probability of y given x and w. And this is now the likelihood, so we're just going to put it in the likelihood model, and we're going to learn just as we do regularly. Yeah?
Scene label, it's
the label that we see.
From the model?
From the data.
From the data, so what is yi?
Y is the latent parameter. Yeah. Y is the true label. So we assume that there are true label for every sample. But for some samples, the true label got distorted using noise. And so we see Z instead of Y. OK, but instead, never mind. Instead, we can say, for instance, for a regression problem, let's just try to learn the noise itself. Let's try to learn the parameter of the noise. So the noise here is modeled by sigma. And then we're going to assume that the noise is going to be different for each point. So we're talking about heteroscedastic noise. And we're just going to take the regular update equation, and we're going to add noise to it. We're going to use the noise. And this means that the network is not outputting just one neuron. We're going to output 2 neurons, one for the mean, which means the predicted label, and one for the variance, one for the standard deviation. And you could also combine those two. You could combine dropout in order to measure the model uncertainty, and you could combine it with, for instance, adding noise output to predict the variance, to predict the data uncertainty. OK. So this was an overview of what methods you have in general to capture uncertainty, both model uncertainty and data uncertainty. And I'm going to talk very shortly about what we do with those things in Taboola. So Taboola is a discovery platform. This means that we have some user that is reading a specific article, and we want to try to estimate what is the best article to give the specific user in this specific time. So given a user and a context, we want to find the best article or the best advertise. to give to the user. And this is modeled as a click-through rate estimation problem. So we want to estimate the CTR of each item that we can give the user. And then we want to choose the items that have the highest CTR, which means that they have the highest probability of the user to click on those items. OK. So instead of just outputting the CTR from the model, we could output also the standard deviation. And this allows us to do all sorts of things. So each recommendation system has the built-in problem of trade-offing between exploration and exploitation. Exploration means that you want to collect new information about the world. So for instance, I get a new item, and I've never seen this item, so I don't know anything about it. I could know things like the text or the image of these items, but I know nothing about which type of users like these items, which type of context works best for this item. So if I don't have this information, I want to start showing this item to people, to different people, a different context, in order to have this information about this item, and this is called exploration. Exploitation just means, OK, I have a whole bunch of items that I know things about, and I want to give the best items that I can, given what I know. And this is already also a trade-off that is very common in reinforcement learning when you want to trade-off between exploration of the agent and exploitation, between the agent exploring its environment and between the agent trying to choose the actions that maximizes its payoff. So once we have the standard deviation, we could use it in order to make decisions about this trade-off. We could, for instance, say, well, this item has a very, very high standard deviation. So this means that we don't know a lot about it. So maybe we want to start showing it more, to collect more information about this item, even if it doesn't get a very high CTR, because we want to try to figure out what's going on here. But items with very low CTR and very low standard deviations, maybe we just don't want to show it. Another thing we could do is debugging our network. So we could ask ourselves, are we modeling the right things? We usually talk about deep learning, and we say, OK, so now we don't need to do feature engineering anymore. How lucky us. But at least at recommendation engine, and also some other domains, let's go. In these domains, you didn't really get rid of the feature engineering part. You still need to try to find the best features and try to find best representations for different aspects of the data. So for instance, if we have a sub-network or some model that takes a title of an article and make a representation of it for the other model to use. And we want to ask ourselves, is this representation good? So we could use some visualization and stuff to look about it, but we could also look at the standard deviation. And we could say, let's start taking off words from the title. And let's see what happens to the standard deviation, what happens to the model uncertainty as we remove some of the information that we have in the title. And if the information in the title is very important, and we model it in a good way, then it means that as we remove more words, our uncertainty, the uncertainty of the model should increase. But if we see that we can remove words and nothing happens to the uncertainty, then it means that either the information in the title is not important at all, or it means that we don't model things right. And you could also think about it as a way to do feature selection. You can think about it, let's see which features they can remove, and affect the confidence of the model in a very serious way. So not just looking at the performance of the model, but also looking at the confidence of the model. And if we removed features and the model has become very not confident, then it means that this feature is very important for the model. One last thing that I'm going to mention is in recommendation. Yeah.
What do you mean by removing a feature?
So that's sort of a classic feature selection. It's very heavy, so you don't really want to do it, but it's just another way to think about the same problem. You could say, let's not use this feature in the training and see what happens. And now we could not use a different feature and see what happens. And this is a way for us to start to understand if a feature that we thought is important is indeed important. So one last thing is, in recommendation engines, you have a problem of noisy labels, which is built in. It's not even a thing of how you collect the data. Because, OK, so if somebody clicked on something, then I know that it's probably interesting for him. But let's say that I showed a user, I presented it with a specific item, and then he didn't click. What can I know about it? Is this indeed a negative label? I don't know, because maybe he didn't click because he just wasn't in the mood now. Maybe in some other context it would be OK. Maybe he didn't click because he just didn't see it. He didn't go to this part of the page, or he just ignored it. Maybe he didn't click because it's really interesting for him, but he doesn't have timeline. No. So all the negative labels are very, very noisy. And we could think about modeling this noise. And instead of trying to optimize using, for instance, maximum likelihood, let's say we have a distribution over the labels. And we have a distribution that the network is outputting. And then let's try to optimize using KL divergence. Let's try to match those two distributions. So this is just something we're playing at. It didn't get very good results so far, but it's just an idea. OK, so I think, yeah, that's all I wanted to talk about. But if you're interested in this topic, this is pretty much the book that I always recommend everybody to ask me anything about a book in machine learning. It's a really, really good book because it talks about all sorts of models from a probabilistic point of view. And you don't really see this point of view very often. You could get through, I think I did about 5 courses in machine learning in the university without seeing this point of view for the same model that I've already learned. So it's really interesting, and also it's very, very Bayesian, so it has good introduction for Bayesian learning and for other things that are related to it, and it's very well written. And NIPS last year, and I think even the year before, had a workshop about Bayesian learning, and it had Bayesian deep learning, and it had some talks with titles like, is Bayesian deep learning the best thing in the world? So you definitely want to see it. And Yarin Gal, which I mentioned all across the talk, because he did really a lot of work on this subject. So he has some blog posts which are pretty nice. They are written well, sort of like academic papers, so you need to bear this in mind. And he has an entire thesis on the subject, and I think he writes really good, so you should read it. And this is all a bunch of papers that I briefly mentioned during the talk, so you're going to get the presentation, I think. So if something was interesting to you, you can just look at it. And that's it. OK, so just one last thing that I want to mention is that Data Hack is hackathon about data science and machine learning. Aviv is doing the woo thing again. It's going to take place in October 25 to 27. It was a really nice event in the last couple of years, I think, and we hope that the next event is going to be even nicer. So the registration is opening tomorrow, and I really hope to see you there. That's it.